I really thought it'd be a fun thing to have October in every video at the start, but she's just not moving. She's just out. All right, but there she is. Let's get into graphical behavior of functions. The last one for this section. And we got a lot of definitions here. I think some of these definitions are kind of should make sense, hopefully. So a main thing to talk about, we have informal and formal definitions. I'm not going to talk about the formal definitions, but you have them in your notes. We should always think about this from left to right. Right? So from left to right, from before to after, that'll make all of this make a little bit more sense. So a function's increasing if the function values increase from left to right. So again, as the inputs increase, that means from left to right. So if it's going up, as it goes to the right, it's increasing. The average rate of change, if it's increasing, is it going to be positive or negative? It's going to be positive. One way that you can think about that is that our earlier parabola example, you remember that? We looked at the average rate of change here. If it's increasing, average rate of change will have a positive slope. Okay. Technically, this parabola is actually decreasing for a little bit and then increasing. Let's not worry too much about that for that example. And again, decreasing is very similar. If you go from left to right, if things are going down, then it's decreasing. Okay. Well, let's do an example. And again, the average rate of change is going to be negative if it's decreasing on that interval. So let's look at this graph of this function p of t. So t is our x-axis and p of t is our y-axis. Maybe we're looking at time and number of patients or profit or something like that. On what intervals does the function appear to be increasing? And so, again, I said left to right, and you probably thought, yeah, Jason, left to right, duh. But it's very tempting for you to say, oh, look, it's increasing over here. But it's not. Why? If I try to say it's increasing over here, that's only increasing from right to left. We always have to think left to right. So I know there's an arrow up here, but think left to right. And as we go left to right here, it's going down. All right. And it's going down and it's going down and it's going down and it's going down until here. Then it starts going up again. Okay, so we're asked about decreasing and increasing. Well, we said it's decreasing on that first chunk. What's that first chunk? Well, forever, right? We can go forever to the left and we still have this shape. It's actually decreasing all the way from negative infinity up to an input value of 1. At 1, it's flat. When x is 1, right here, it's neither increasing nor decreasing. It's flat. It's not going up or down. So 1 is not going to be included. And in fact, when we talk about increasing and decreasing intervals, these intervals are always open. Always open, always has parentheses for increasing and decreasing. Because the transition points are always flat if it's continuous. Technically, if it's differentiable, but we won't get into those. Okay, where else is it decreasing? Again, thinking from left to right, starts falling over here, right? And it's falling and falling and falling. So it's also decreasing from 3 to 4. We'll connect them with a union sign, just like when we talked earlier with interval notation in last section. As we go from left to right on this graph, is it decreasing anywhere else? No. Everywhere else, it's increasing. I have no idea what color I can use to make this legible. So again, if we start at 1 and go to the right, this looks like the same color. If we start at 1 and go to the right, oh no, it's frozen. I've crashed my PDF. If we go from an input of 1 to an input of 3, notice the function is going up. Thank goodness it caught up. All right. Over here, it's all going up. It's going up. It's going up. So it's going up. Add an input of 1 up to an input of 3. Yeah, this is the same color almost. And then once we get to 4, it starts going up again, and it goes up forever. It also goes up again from 4 up to positive infinity. We can connect those with a union sign as well. These are the intervals where it's increasing and decreasing. Oh, I could have used blue. All right, that's increasing and decreasing. Increasing, going up. Decreasing, going down. From left to right. Okay? So be especially careful on the left side of any graph. Always remember left to right. 2 more definitions. I lied. 3 more definitions. So if something goes from increasing to decreasing, it's called a local maximum. It was increasing, and at this point, it starts going down. It's a local max. That makes sense. Think of a roller coaster. Relatively the top of a part of a roller coaster. If it's decreasing, it's going down. And if it switches to increasing, have arrows reminding us left to right. That's a local minimum. And if we want to talk about local minimum or local maximum, we call them local extrema. Local extremum is the singular. Local extrema is the plural. So in example 10, where I say find and classify the local extrema of P of t from example 9, this says go to that last example and tell me where the local minima are and the local maxima. And it's just going to be the transition points where the graph changes from red to a slightly different color that looks like red. I think it's like fuchsia or something. Again, we go from decreasing to increasing here. That's a local minimum. Increasing to decreasing here. That's a local max. Decreasing to increasing here. That's a local minimum. So we have 2 local minima, 1 local maximum. So this is the point, maybe it's a point 1 comma, I don't know, about -0.5. Estimate. This is the point 3 comma 1. This is the point 4 comma, I don't know, 0.75 or something. Estimate. And we'll use that as our answer. Now the wording of this is a little precise. There's going to be a local minimum. The minimum is the y coordinate. The local minimum is -0.5. And it occurs, let's say when. It occurs when our input is +1. Our input's t, actually. We're talking about the minimum value of the function, right? So this is the function value. So when we say, what's the local minimum? We want to find the minimum value of the function. So the local minimum is the output. But then we often talk about when that minimum happens. There's a local minimum of -0.5 when t is equal to 1. And there's another local minimum at an output of 0.75 when t is 4. And 0.75 when t is equal to 4. That's a good way of writing your answer. There's a few ways I'll accept, but I think this is one of the best. And there's a local maximum. The local maximum is the maximum function value locally is 1. Locally, the top of this hill is 1 unit high when t is 3. That's the best way to answer. Sometimes people answer with ordered pairs. This is really the best way. It gives the most information in the clearest way. It's extra words, which I don't love, but clarity is good. Do one more example. This table that I have messed up so many times. T is the years after. And C is the cost in dollars per gallon. I literally copied this table 3 times. And it's wrong every time. Let's use the same table that we all remember. Find an interval. There could be multiple, but find an interval on which the function appears to be decreasing. So there's 2 points, and we'll get to the second part of the problem later. Where do we think this function is decreasing? Well, where is it going down? When is it going down? It's decreasing in a couple places, but maybe a good example is it's decreasing from 2018 to 2020. But you could easily make this as your answer. Or this could be your answer. All right? There's a few answers. Just choose one, it says. So it's decreasing from 2018 to 2020. That's just one possible answer. And it says estimate any local extrema. So how I like to do this is I like to draw little arrows. At 0, is it going down? Yes. We're going down. We're going down. We're going down. All right, so we're decreasing from 2014 to 2016. And then we start increasing, right? Now we're increasing, increasing, increasing until 2018. And now we start decreasing again, right? These numbers are now going down and the numbers are start going up again. So remember what we said for local extrema. A local minimum is when it's going down and then it starts going up. Local maximum going up and then it starts going down. So if you draw a picture like this of increasing and decreasing, then it's a lot clearer where those transition ports are. This is going to be our local minimum. This is going to be our local maximum. This is going to be another local minimum. All right. We'll say local min of, remember how we phrase this, of the output, $2.59 per gallon in 2000, and 2 years after 14 is 2016, and a local minimum of $2.45, this other bottom red point, per gallon in 2020. Local max is that top red point of $3.14 in the year 2018. That's our answer for this part. So again, it's local max. Yes, gas was a heck of a lot more expensive in 2022, but that's not the peak of the hill. Saying this from 2023, okay? 2022 was not the peak of the hill. Local extrema is just the top of a hill or the bottom of a valley. Not the highest point, not the lowest point. They're locally the max and locally the min. Okay? Right? Graphically, local extrema are not necessarily the biggest or the smallest. In this case, this actually is the smallest. But that's another term. That's called absolute or global extrema. And we're not talking about that right now. Okay, so you should have everything pretty good to go. Let's do a try it now. Use Desmos to graph that. You click on that link. It'll take you right here. This is Desmos. I like having it in reverse contrast, but you don't have to. And it says use Desmos to graph this function. F of x is x cubed minus 6x squared minus 15x plus 20. And you might see, well, I can't see very much. So if that's the case, click on the little wrench here and zoom appropriately. So how do you think we need to zoom this appropriately? We can also click and drag around. Oh dear. Sorry. Well, it's going off to the top and off to the bottom. So our x's are maybe fine, but we need to see bigger y's and smaller y's. So let's make our y's. Let's go down to like -15 and +15. Okay, that's a little better. We need to make the y. We need to see more y's. So let's go down to -25. Still not enough. Let's go down to -50. Still can't see the bottom. -100. Now we can see the bottom. Let's say +50. Okay, so you're gonna have to guess and check, right? And if you just use the scroll wheel and zoom out, it'll work now. But if you use the scroll wheel and zoom out, then it's also zooming out in the X's, and it might not help. Actually, we'll show that actually. Right? We go back to our regular Y's. If we just scrolled out in both directions, like you can kind of see it, but sometimes you won't, and it's much uglier. So I recommend editing it this way, but you do have options. All right. Anyway, the question asks you, if I can find my tab again, my window. Question asks you, estimate the local extrema and the intervals of increasing and decreasing. Oh no, I did it again. I'm a mess over here. Okay, so where is it increasing and decreasing? Remember, it's always from left to right. So you think you're all the way down here. As you're moving to the right, we're going up, we're going up, we're going up, we're going up, we're going up until we get to here. Okay. So we're increasing all the way from -infinity up to an input, increasing. When we use interval notation, interval notations are about the inputs. Local extrema, usually about the outputs. So it's a little confusing because it's kind of both. But interval notation is telling us the inputs for which it's increasing. And it's going up to an input of -1. It also kind of sucks because interval notation a lot of times looks like an ordered pair, right? An ordered pair is just two numbers in a parentheses. An ordered pair looks exactly like this, but this is an interval, okay? And now it starts decreasing, right? Decreasing when x is -1, and it's decreasing, 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 all the way until this x value of +5. So it's decreasing from -1 all the way up to +5. And again, at -1, it's neither increasing nor decreasing. At an input of -1, it's flat. All right, and then after an input of 5, it starts increasing again forever. If you're curious whether it's actually forever, zoom out. Yeah, it's forever. Okay. So it's again increasing from 5. Whoa, that's not a 5. Nice try, Jason. From 5 until infinity. We'll connect those two intervals with a union sign. That's increasing and decreasing. What about the local extrema? Well, the local extrema are when it switches. So you can see, sorry, I keep switching it, flashing lights at you. It's switching at an input of -1, right? It's switching at an input of -1, and it's switching again at an input of 5. Let's get our syntax right. We'll have a local min. What is the minimum value here? The minimum value that this function gets locally around these parts is -80. When does that occur? When x is 5. We also have a local max. What's the max value? Well, the max value, again, just locally, just around these parts. It's not Mount Everest, but it is Mount Rainier or something. Not the tallest, but certainly the tallest around here is 28. When x is -1. Okay. There you go. Hopefully that's what you got. I forgot to tell you to pause the video, but hopefully you did. It's try it now, not watch it now. I don't know. Let me know if you have any more questions. We'll do some more practice after this. Bye-bye.